Hello everybody, in this lecture we will be solving 1978 IMO problem number 3. Here is a view of this problem. The set of all positive integers is the union of two disjoint sets. Let's call this first set as F and the second set as G. As you can see, the elements of the set F are monotonically increasing, as is the case for the elements of the set G. And finally, the elements of the set G are described in the following fashion, and as a result, the elements of F will fill out the void in the sequence, right? So once we identify which elements, which positive integers are part of G of n, are part of the set G, then the remainder will be the elements of F, and we can easily list those elements. So what I will do next is let's make a few observations. So first of all, we agreed that F union G will span the whole the set of positive integers. So my goal will be, first let's try out a few values, because eventually we need to calculate F of 240. So what I have in mind is I will have the real line, and I will start putting the real numbers on that line, and I would like to identify what each of these positive integers are associated with. Each of these numbers are either in this set or in the other set. Okay, so let's start with what will be 1? Is it going to be F of 1 or G of 1? One of them would have to be 1, right? Like I said at the beginning, so this definition is clear, so we can try to see what G of 1 is. If G of 1 is 1, then it is. If it is not, then it means F of 1 would have to be equal to 1. So G of 1 by this definition is equal to F of 1 plus 1, and notice that both sets only assume positive integer values, suggesting that this expression here is greater than 0, implying that this whole thing is greater than 1. So this gives us, the conclusion follows immediately, F of 1 is equal to 1. That's it. So we know that this guy is, let me write it with a subindex here. That simply means F of 1. Okay? So then next we can now calculate G of 1. So it is F of 1, but F of 1 is just 1 plus 1. F of 1 here is 1. 1 plus 1 is equal to 2, and that's the value for G of 1. So therefore here we have a G of 1. I will remove the brackets from now on. Okay, so let's calculate G of 2, which is simply F of 2 plus 1. Now one might wonder if G of 2 might actually equal 3, the next number. Can it be G of 2? So let's see if that's reasonable. So if we set it, so we are testing it. If it's equal to 3, that would imply F of 2 is equal to 2, but that's impossible, because F will never map a value to 2, because that's already taken by G. So that's a contradiction. So therefore this assumption was wrong, implying that in fact it is F of 2 which is equal to 3. So let's put it here. F of 2 is equal to 3. But then this implies as a result that G of 2 is simply equal to F of 2 plus 1. But F of 2 we agreed was 3, so this is just F of 3 plus 1. And finally that gives us F of 3 plus 1. So wow, that's even more shocking, because we haven't even defined F of 3 yet. So F of 3, it must be the case that F of 3 is the next guy. So this has to be 4 then. So we have 4 plus 1, which is equal to 5. So that gives us a clue about what G of 2 is. G of 2 is just 5. Now we can move on, proceed in the following manner, right? So G of 3 would be F of 3 plus 1. Luckily we already calculated F of 3. F of 3 was just 4 here. So 4 plus 1. Wow, so therefore we need to first identify what F of 4 is, and which is it has to be the next number in line. And so therefore it is 6 plus 1, 7. So therefore G of 3 is just 7. And I can keep proceeding in the following manner, right? So let's continue, I guess. So I did g of 3, let's do g of 4. I want to proceed a few more terms until everyone has a good understanding of what's going on. It is just f of 4 plus 1, but we have already established f of 4, so it is just f of 6. F of 4 is just equal to 6 plus 1, and that's a problem because I don't know even f of 5, so that for 8 has to be f of 5, and f of 6 have to be equal to 9. So 9 plus 1, which is 10. So therefore 10 is equal to g of 4. And we can continue. As you can see, in each step, what I do is I try to describe the g of the next, like g of n, and as a result, the sequence f will complement the whole thing. So which is just f of 5 plus 1, but f of 5 we agreed is 8, so f of 8 plus 1. That's a problem. I know only f of 6, so f of 7 is the next guy. F of 8 is equal to 12. And so therefore this is equal to 12, suggesting 12 plus 1 is 13. So g of 5, g sub 5 or g of 5 is just 13. G of 6, one more, and then let's go to see if we can figure out the pattern. So f of 6 we agreed was 9, and f of 9 plus 1, f of 9 is just the next term in line, so this is f of 9, which is 14, so 14 plus 1 will give us a 15, and so on. I can proceed in this fashion, and so we got 15 as well. This is g of 6, for instance. It is obvious that we will never have, all the time it happens to be, when I do a few observations here, one of the observations I realize is that the g's are always followed by f's. I might have to prove that. But it's not necessarily the case for f. F is sometimes followed by an f, but sometimes it's followed by a g, right? But it is the case that g's are always followed by f, so it's no surprise that the next term probably has to be, so 16 has to be f of 10, right? There's no way that I can get 16 for g of 7, because g of 7 eventually would be f of 7 plus 1, but so 1 less than that always is g, so there's no way that f will map an element to it. Like, I will get a similar type of contradiction that I got here. So therefore it implies that the values of g's are always followed by f's. Okay, so what I will do next is I want to, having made so many observations, I want to now constructively count what g is. So let's see if I can find a closed form formula for g, which I hope I will, because so far I have a very good understanding of what's been going on. So let me start over. Hold on. Okay, so let's assume now. So therefore I want to now find a closed form for g, and then eventually for f as well, for the sequence f as well. So let's assume that f of n is simply equal to, let's say, k. Then I want to observe what's happening to these two disjoint sets. So have a look at f of 1, f of 2, all the way up to f of n, if you will, right? Which is just f of k, right, by the way. So consider this set, and consider also this set g sub 1, g of 1, g of 2, all the way up to g of n. Okay, so I claim that this, the union of these two sets is simply equal to, right, because this guy is simply equal to f of n plus 1. Do you agree that, so the union of these two sets is simply equal to all the positive integers, starting from 1, 2, all the way up to, I would say, f of n plus 1, right? f of n plus 1. Or if you will, this is just g of n, right? So all the positive integers 1, 2, up to g of n this is the disjoint union of these two sets is equal to this set here. So therefore, it's very easy to count g of n as a result, right? 1, 2, all the way up to g of n. It's very easy. G of n is simply the sum of the number of elements in this set plus the number of elements in this set. How many elements is in here? F of 1, f of 2, all the way up to f of k. There's k elements, clearly. Plus, how about here? How many elements here? G of 1, g of 2, g of n. Of course, there's n elements here. So therefore, yeah, so we have a closed form where k is obviously equal to f of n. So I have my first really nice formula, right? So this formula is crucial for me. And this will enable me to find out a new formula. So let me call it formula 2. Notice that from the first one, we get g of n is equal to k plus n. But if I replace g of n with its definition, f of n plus 1 is equal to k plus n, and replace f of n with k, this gives me my second formula. So this is the first formula, g of n is equal to k plus n. And secondly, we would get f of k plus 1 is equal to k plus n, implying that f of k is equal to k plus n minus 1. And that's my second formula. And thirdly, let's prove an observation that I have already made. So consider g of n, which is already an element in the set, which I called it as g here. So g of n is in g, implying that if you apply the definition, g of n is equal to f of n plus 1, this would imply that g of n minus 1 is equal to f of n. But this is the value that the function f takes at this particular occasion. F of n is equal to k, right? F of k. So, but this implies that g of n minus 1 is in fact a member of f, right? So this implies that g of n minus 1 is a value taken by the function f. So is in f. So whenever a value g is in g, then the preceding term has to be in f, suggesting that, implying that no two consecutive elements in g, right? So we've made this observation early on when I analyzed this table, this real line, right? But that's perfect because this gives me my next result, so the third result that I was mentioning. So therefore, if you have the number g of n, the previous number, so g of n, we defined this as k plus n. We know that the previous number is f of k, so therefore the next guy in the set f, capital F, will be f of k plus 1, and it is simply equal to this guy plus 1, k plus n plus 1. So now I have enough formulas to establish what I need. So now let's go back and let's try to establish f of 240. So I will first try to use this as much as I can to recursively build up on the f, and as I approach closer to the formula, to the number 240, I will use this to make some refinements to the result. So for the computational part, let's begin on this side. So using this formula, so far let's start with an initial value, probably for instance, let's start here. F of 2 is already equal to 3. So I know that, let's write that down here. F of 2 is equal to 3. So then, recall that our initial assumption was that k is equal to f of n. Let's write that down. Whenever k is equal to f of n, we know that f of k is equal to this, right? So if f of 2 is equal to 3, that means f of 3 is simply equal to k, 3 plus n. N is the domain, the thing that is mapped to k, so that therefore it is the 2 that I have minus 1. So that's just a 4. Now f of 4 is simply equal to 4 plus the 3 minus 1, which is 6. F of 6 is equal to 6 plus the previous one minus 1, which is 9, and so on. So let's do it a few more steps until I reach very close to the number 240. 9 plus 6 minus 1, which is 14. F of 14 is going to be equal to 14 plus 9 minus 1, which is 22. F of 22 will be 22 minus 14 plus 14 minus 1, which is 36, 35. Let's move on to this side, I guess. F of 35 is just 35 plus 22 minus 1, 57, 56. F of 56 is equal to 56 plus 35 minus 1. That's just 55 plus 35, which is 90. We have f of 90, which is equal to 90 plus 56. 146 minus 1 is 145. A few more, I guess. F of 145, which is 145 plus 90, 235 minus 1, 234. Whoa, okay. The next one will be way higher, right? So f of 234 will be 234 plus 145 minus 1. I won't bother calculating it. It's way too high. So this number is close enough. I have f of 234. So therefore, just this formula by itself will not be sufficient. So let me make use of this formula as well, the next term formula here. So the next term would be 2 more than this. So, or let me write it down here maybe. Okay, so let's write down here. F of k plus 1 is simply k plus n plus 1, right? So let's make use of this. For example, if I use this line, f of 91, one more, is equal to the previous one, which is the 90, plus the one which caused it, which is the 56, plus 1. So which is 146, 147. And then I can, in a similar way, try, would that work? F of 148. Right, so f of 148 is just 147 plus 1, so this is 147. What caused 147 was 91 plus 1. So 147 plus 90 is 237, 238, 239. Right. So this gives me 239, and finally f of 240 as a result is just equal to right. So it is just f of 239 plus 1, and I'm using my my formula here, so that would be 239 plus the thing that caused the 239, which is 148, plus 1. So finally, this is 240 plus 140 is 388. 388 it is. And we got the desired result of 388. That solves the problem. Now, I would like to provide an alternative solution to this. And if time permits, I would like to also come up with a third solution, because this problem is very interesting. In fact, I will make use of a result that is listed as the following theorem. Let me write down the theorem. I believe the theorem is by Beatty. I don't know how to really say that word. But the theorem basically tells us that if you have two irrational numbers, alpha and beta, irrational. So this is a second solution I'm proposing now. Second solution. Okay, so if alpha and beta are irrational, such that 1 over alpha plus 1 over beta is equal to 1, then the striking result, so let's say if then it is possible to come up with two disjoint sets that would span across all positive integers, right? Or put it more rigorously, then we claim that the following two sets, namely the floor of alpha, 2 alpha, and so on, 3 alpha, and the set beta, 2 beta, 3 beta, and so on. So these two sets, they form a partition, a disjoint union of the set of positive integers. So this is really beautiful result. So these two sets create a partition of the positive integers. That's just amazing. let's call this set as F, and the set F and the set G here. A general term for the set F as a result is F of n, which is equal to n alpha, and G of n here is n beta. So if we can find irrational numbers alpha and beta that satisfy this condition, then it's possible to construct such partitions, such disjoint sets that span the whole positive integers. Now, I claim that the two sequences that are given in our problem, defined by this functional form, they form a Beatty or Beatty sequences, right? So, and if we can prove it, if we can find the alpha and beta that generates those two sequences, and if we can show that the alpha and the beta, they satisfy this condition such that their reciprocals add up to 1, then I'm done. And the key is the following. So we have observed that if you look at our first proof, we have observed that G of n is simply equal to k plus n when for k is equal to f of n, right? If I replace k with f of n, I'll have f of n plus n. But this simply translates as the following. So this implies that n beta, if we write it in terms of our sequence, is equal to n alpha plus n, where n is a positive integer, which means it can go inside the floor, n times alpha plus 1, or n alpha plus n, and this will hold for all n positive integers, mean that if such two floor functions are equal for all n, infinitely many of them, it must, and knowing that beta and alpha are irrational, this would imply that in fact each of these has to be equal to each other. Now, cancelling the n's, we have beta is equal to alpha plus 1. Now plugging this here into this condition, so this would imply that 1 over alpha plus 1 over alpha plus 1 is equal to 1. Now we know our sequences given in our problem are Beatty sequences, and if once we identify the alphas and the betas, we would have a closed form formula for the function f, implying that, so we get our very special number that's so alpha comes out as, not surprisingly, 1 plus root 5 over 2. And in a similar way, you can easily calculate beta to be just one more than this, which is 3 plus root 5 over 2. For our purposes, alpha would be more than sufficient. So we have f of 240 now is simply 240 times alpha, and this number here, the floor of this, so which is the floor of 240 times 1 plus root 5 over 2, which is 120, the floor of 120 plus 120 root 5. I can remove 120 from the floor. Root 120 root 5, and now the rest is just the calculator. It turns out that this whole number comes out as okay, so let's write that down. So we have 120 plus, so this number is approximately equal to, if you use your calculator, you would see it is equal to 268.32. And so when I take the floor of this, it would be 120 plus 268, which brings us again to our result 388, as we have found in our previous solution. So that's really beautiful. In fact, this is all connected to the Fibonacci numbers, because the number alpha here, yeah, so this number is the golden ratio. So the same number that that's somehow useful in the Fibonacci sequence. So that gives us an idea that in fact there might be something going on in our sequence, the way that the f function is spread out here, that somehow it is related to the Fibonacci sequence. So I'll just leave it here. You can check the discussions on AOPS to further this idea and to come up with an alternative solution to this beautiful problem. Hope you enjoyed the video and looking forward to see you guys in our next lecture.